Okay, so my name is Aditya. I've been with DICT for just over 10 years now. Uh, my area of interest is in image, signal, and geometry processing, and I therefore okay, I don't develop, but I do use geometry for my work. And so in this particular course, MC 111, there's supposed to be a module on space and structures in space. So since I do use geometry, I thought it's a good idea to talk about some of these things. Assuming nobody else has delivered a class on curvature, I hope you will find it interesting. Today it will be a lot of possibly equations, and I don't know, you might find it a little boring, but this will sort of help us for tomorrow's class, and tomorrow is when I will sort of talk about more interesting and beautiful results. And of course, they will be dealt with without proofs. So, wanted to sort of give you a full combination of derivations, proofs, results, intuitions, and things like that. Okay, so don't worry if you sort of don't get it completely, but the idea is you will see what sort of results mathematicians are after, and hopefully you'll also see the beauty behind the results. Okay, I have purposefully avoided talking a lot about applications, but believe me, there are wide-ranging applications of what we are going to do in these two classes. Okay, so let us start. I once again apologize for not preparing very formal presentation. You can see most of these are handwritten slides, but I hope you'll find them legible. Okay, so now without begin with curvature. Curvature, of course, is a mathematical concept, but it's a concept for which all of us have certain intuition, right? So we first look at curvature of planar curves. By planar curves, I mean curves, right, that you can draw on, let's say, the XY plane. Okay, and curvature sort of tries to measure how curved is a given curve. Okay, so let's start with a very trivial example. So you can see the XY plane that I've scribbled on the slide, and I've drawn a particular curve shown with the red color, and I'm calling this curve by the Greek alphabet gamma. Okay, trivial question. What do you think is the curvature of this particular red curve? This red curve, of course, is a straight line. So what would be your answer? Anyone? Okay. Anybody who answers my questions will get a chocolate when you return to the campus, if it helps.
0.
Okay, 0. Ishan, do you have a mic with you? Be good to hear your voice.
Yes, sir.
Yes, so go ahead.
So I feel the curvature would be 0, probably because
0.
it's completely straight.
Completely straight, right? So that is what I meant by when I said that curvature is something that we all have a fairly good intuition, right? So this is an easy
Sir,
question, and
I think,
uh, yes, go ahead.
sir, I think it's infinite.
It's infinite. Oh, okay, interesting answer. Infinite. Maybe I'll write down these answers. And it is 0. Why do you think this should be infinite? And
Sir,
your name,
we had the
please?
formula of radius of, So my name is Tirth Vadaria.
Okay, go ahead, Teeth.
Uh, I answered infinite because I knew one formula about radius of curvature, that 1 plus dy by dx whole raised to 3 by 2 dy by
Wow.
dx square raised to 3 by 2 and divide by d2y by dx 2.
1 plus dy by dx raised to 3 by 2.
No ma'am, no sir. 1 plus dy by dx square and whole raised to 3 by 2.
Oh, okay. Whole raised to 3 by 2.
D
This
upon
is, oh, okay.
d2y by dx 2.
D2y by. So because d2y by dx2 is 0, you're saying it should be infinite. Right, Teeth?
Yes sir. That's why I answered infinite.
Right, but I think there's already a comment in the chat that you can read. Divyansh says, radius of curvature and curvature are different things. So what is the difference, Divyansh?
Sir, means curvature is how much is it is means curved means you are talking about that intuition that it is a straight line, and radius it means that if it is drawn into a circle, then
Right.
the radius will be infinite.
Okay. Right. So the thing is, the radius of curvature is if I sort of draw a circle, right, which is tangential to this curve, right? What is the largest circle? Largest in the sense, largest circle, sorry, circle with the largest radius that I can have the circle being tangent to this curve. So of course you're right. I mean, you can, I mean, the straight line itself can be seen as a circle with infinite radius. So in that sense, radius of curvature for this is infinite. But again, curvature is sort of inversely proportional to that radius. Okay, so as radius of curvature is concerned, you're right, it's infinite. The curvature is sort of inversely proportional to the radius of curvature. So as far as curvature is concerned, Ishan is right. In principle, you're also right. You have the intuition in place. Because basically, the straight line in some sense is defined as a curve which does not curve at all. Sort of going in a circle here, but still, again, I'm appealing to your intuition. And therefore, I'm sort of stating this, that given a straight line, you would sort of all agree that this line is, or this curve is not curved at all. And so the curvature should be 0. Okay, let's move
Okay sir,
ahead.
got it.
Okay, so I hope I am not forcing this on you, but I'm actually convincing this you. So, okay, anyways, let's sort of proceed. So then, based on this intuition, I can sort of define curvature, right, as a measure, right? It measures how the given curve deviates from being a straight line. Okay, so again, let's take examples of 3 curves. One is black, the other 2 are circles, of course, of different radius, right? So question is, which of these 3 has the highest curvature?
Sir, the blue
Which is
circle.
the most curved curve amongst these 3? Anyone?
Sir, the blue circle.
The blue one, right? This is the most curved curve amongst these 3, because if we were to compare this with the straight line, it sort of is it deviates the furthermost amongst these three. Okay, so again, this is just to emphasize this statement that I made, that curvature measures the deviation of a curve from a straight line. Okay, so more it does not resemble a straight line, higher should be the curvature. The other thing is, so let's say this is another curve that is given to you, right? And let's look at the curve at three of its points. 3 points are marked by different colors, blue, green, and red. Right? Do you think the curvature at all these 3 points is one and the same?
No, sir.
No, right? So which is the least curved
Blue.
point with the least curvature?
Blue one.
Blue one, right? All of you agree. And the most curved point?
Red.
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 So fine. So what does this imply? Right? It implies that curvature of a curve, first of all, it differs from point to point, right? And therefore, curvature is what we can call a local concept. So if I'm trying to find the curvature of the curve at this point, it doesn't really matter how the curve appears outside a small region of the curve around this point. Even if I change the curve from this to something like this, right? The curvature at this point will still remain the same. So you can sort of conclude that it's a local concept. Agree?
Yes, sir.
Yes, sir.
So now, equipped with these sort of three intuitive concepts, right? As of now, curvature is still an intuition for us. Let us now try to figure out, if I give you a curve, can you give me equations for computing the value of the curvature? Okay, as of now, we have been dealing with curvature only relatively. This has less curvature, more curvature, not curved at all. Let's now try to come out with an equation that gives us a number. Okay, and since you are doing the course which is sort of calculus, so I'm going to use things you have done already. Okay, so let's first work with the straight line and see how we can get an equation that gives us a zero, right? So equation of that straight line, all of you know, is y equals something like mx plus a, where a is the intercept. Okay. Now, instead of using this representation of a straight line, right, I would want to describe this straight line as if there was a point or a particle, right, which moved on this curve. And I'm going to describe this curve by describing the positions of this particle as a function of time. Okay. So for example, I can say that the x coordinate at time t is exactly equal to the time. So xt is t. Once I use this, then yt can be obtained by just plugging in the x coordinate function in this equation over here. Okay, so my y of t would be m of xt plus a, and since xt is t, so I have y equals mt plus a. Okay, now since this is describing the motion of a particle on this line, right, I can also compute velocity, right? So what would be the velocity? Trivial, it's just 1 comma m, where m is the slope. How about the acceleration? All of you have just finished your physics courses last year. So the acceleration would be 0, right? Suppose it's a vector. The acceleration vector would be 0, and it would be 0 at all times t. Now, roughly see that I want curvature as a single number, right? It's a single number, measures the deviation from a straight line. It cannot be a vector. Can I sort of set the curvature equal to the length of the acceleration vector? Okay, so in this particular example, what is the length of the acceleration vector? So 0, 0 is basically origin, so the length is 0, right? Right. So will this work as a definition of curvature?
No, sir, because you initially took x is equal to t, and it depends on this.
Right. So can you give me a counter example?
When you take x is equal to t square, then it will be different.
Right. xt t squared. What would yt be?
mt square plus a.
Mt squared plus a. Right. And what would the acceleration vector be?
M times 2t, m2m, m2m.
So second derivative of x would be
Sir,
first
2
derivative
comma
is
2m.
2t.
right, 2 and 2m. Right?
2m.
And so this surely is not 0. Okay, so you're going to end up in an issue if we use this definition. So what is wrong here? You also write.
But sir, curve is also not straight line, na?
So is the curve not a straight line? Can you plot this curve? So let's say t goes from 0 to 1. Then it will be easy to draw. It's 1 comma 1. Right. When t is 0, at what location is the particle? Okay, let's for now assume this a is 0, just to make our lives easier. So x and y would be, when t is 0, x and y would be 0, 0, right?
Yes, sir, it will be a straight line.
It would be a straight line. Agree?
Yes, sir, agree.
Okay. Right. So since it's a straight line, again, appealing to our intuition, we want that whatever equation we come up for curvature, it should give you a 0. So why is this happening? Your velocity here is 2t to mt. Now, okay, again, if you recall, I don't know, this possibly these days is not done in 12th class, it's done much earlier, right? Velocity, acceleration, so on and so forth. I don't remember my school days any longer. Acceleration is due to what?
Change in velocity.
And velocity has two things,
Magnitude and direction.
right? So what is the magnitude of velocity called?
Speed.
Right. So if my speed changes, will I have an acceleration?
No, sir.
So change in
If the
speed
direction does not change.
right. So okay. So change in speed. How many of you agree that it will not lead to acceleration? So okay, let's take this example itself. Right. Velocity, is the direction changing? what is the speed here?
No, direction is same,
We
but
have computed. What is the speed?
magnitude is changing.
It's changing.
So can you compute the speed for this velocity?
Under root of 4t square plus 4mt square. 4m square t square.
4 common, then 1 plus m squared, right?
Yes.
So is the speed changing?
Yes, sir.
It is, right? It's a function of t, obviously. Is the direction changing?
No.
No, right? So here in this example, m I've assumed to be 1, right? So the direction in which I'm traveling is. So then what is the source of this acceleration? Why am I getting an acceleration, a non-zero acceleration? Is it because of change in speed or change in direction?
Change in speed.
Change in speed, right? So therefore, of course, change in speed also, of course, contributes to acceleration. And the other thing is
Change in direction.
change in direction. Now, can you see what is the issue with our definition, our proposed definition of curvature? Is the length of the acceleration vector.
It should be length of radial acceleration vector. Because
So,
the
out of these two sources, which is the source we should consider and which should be the source we should ignore?
change in direction, consider change in speed. We do not have to consider.
Right? Because what does curvature again intuitively measure? Measures how the curve deviates from being a straight line or how curved it is. So what should matter is how much should a particle have to change its direction of travel and not what is the change in its speed. Got it?
Yes.
So can we figure out a way, right, so that when we compute the length of the acceleration vector, the acceleration should not be due to change in speed. Okay, once we take care of that, then whatever is the acceleration will be only due to change in direction. Right? That's the idea. So gamma, right, is basically describing the position of the point in the xy plane with respect to time. Time, let's say, takes on values between some alpha beta interval. Okay, so if gamma t is given by these two functions, x of t, which represents the x coordinate, and y of t represents the y coordinate, right? If we say that the length of its velocity vector, which is basically speed, is always 1, okay, then we say that this curve, right, represented by gamma, is a unit speed curve. Okay, once again, means that if the point moves on the curve always with speed equals 1 unit, right? It, in some sense, it doesn't have to be 1, it has to be constant speed. Okay, but constant can be any arbitrary number. So just as a convention, we always use the speed as 1. Okay, so for all points and at all times, the point is moving with the same speed of 1 unit. Okay, then this curve represented by gamma is called a unit speed curve, which means that if I compute the acceleration of gamma, right, then the only source is the change in direction. And so for such unit speed curves, I can define the curvature as just the length of its acceleration vector.
Sir, so basically it is a circle in particle moving in circle,
Okay.
which has no tangential acceleration, only radial. That's why.
So see, given a circle, have a point that moves on it, which also has a non-uniform speed, isn't it?
But we have given uniform speed here, one.
Yes. Are you asking why?
No, we can relate these two by this example, the return part. Because
Right.
when we compute the formula that you have written at the last,
This one.
it is the total acceleration in normal forms. But here we can assume that the speed is constant, so tangential acceleration will be ultimately zero. So
Yes.
radial will be
Right.
the only one.
Exactly. Yes.
Okay.
But if it's a circle, right?
Yeah.
So we can sort of take an example here. So let us say gamma t is cos of t and sine of t. What is this curve? And let's maybe generalize this a little bit. R cos of t and R sine of t. What is the curve that gamma represents?
Circle.
Circle or
Radius r at center
radius
0, 0.
r? Right? Good. So what is the curvature at any point of this circle? So gamma dot t or d gamma by dt would be quick gamma dot t.
Minus r sin t, r cos t.
Now what we should do? So is this suitable for our definition?
Sir, if we are only considering change in direction, shouldn't we work in terms of angle?
Sorry, in terms of?
Wouldn't the angle also change here? T, that angle cos t sin t. You have said that it is constant because while differentiating, we are not. No, sorry, sir. Sorry, sir.
Okay. So is this valid for our definition of curvature?
Sir, is this unit speed required, or we can
That's what,
say any
that's
constant
exactly my
speed?
question. Is it constant?
Sir, the unit speed is not always there, so we need to change the formula.
No, it's never there, isn't it? Unless r is 1, of course.
Yes, sir.
Yes,
So
sir,
what
it is
we do?
constant, but it is r.
Will this work?
Yes, sir.
It is gamma 1 dot t.
Minus sin t comma cos t. Sorry, minus sin t by r comma cos t by r.
Okay. So unit speed?
Yes, sir.
Right. So then what should I do in order to compute the curvature?
Again differentiate.
Again, differentiate. So So this dot represents d by dt. Okay, you don't get confused with the double derivative of gamma 1t.
Minus cos t by r divided by r. Uh,
Minus sin t by r.
minus sin t by r.
So what is the curvature? Length of
1
this
by r.
vector 1 by r is again a line which aligns with our intuition, right? Larger the circle, smaller the curvature.
Yes, sir.
Okay, so as of now, I hope you agree with what we are doing.
Sir, I don't get why the length of acceleration vector gives us curvature.
It does not always give only. So why is acceleration present, right? It's present due to one of these two sources. Either there is change in speed or there is change in direction, right?
Yes.
Now, what is curvature? Intuitively, it's like if you are sort of driving a vehicle on a particular path, how much do you have to turn your steering wheel in order to stay on the path? Right? But of course, while traveling on the path, you can also accelerate or decelerate. That also is going to contribute to the acceleration. Okay? But what we are trying to capture is how much does a vehicle have to turn in order to stay on the path at each and every point. That is what is characterizing the curvature, isn't it?
Yes.
So therefore, I am only interested in the acceleration due to change in direction, not in the acceleration due to change in speed. So then the obvious question is, how do I factor out the acceleration due to change in speed? And factor it out by imposing this condition that no, you are not allowed to accelerate, I mean, change the speed at least.
So, sir, what is the reason behind taking acceleration? Means we can also take speed to, means speed has also two things, magnitude and direction. Velocity has also two things, magnitude and direction.
Yes,
Why
but
didn't
so for
we?
example, in this curve, what is it that you want to capture? Is it the velocity? So what would be the velocity given here, right? The thing is, I can travel the same path with different velocities, isn't it? So you can see here the velocity of gamma, right? If gamma describes the motion of, let's say, Ishan, right? At what speed is Ishan traveling?
Gamma dot.
The magnitude of gamma dot, right?
Yes.
That's R. Am I right?
Yes.
Whereas, let's say Divyansh travels, or his motion is described by gamma 1. Okay, so what is the speed with which Divyansh travels?
1.
1.
1. But are they traveling on different paths?
No, sir.
No.
No. So we cannot rely on the length of the velocity vector, right?
Okay.
Or sir, we can also say that
Sir,
a double differentiation of any function shows a change in slope of that function, and slope is the direction. So change in direction of that means the it is relying to that definition you told us, that how much the curve is deviating from the line.
Exactly. That's what I'm trying to say. I'm trying to capture the change in direction, and acceleration is one quantity that captures that, isn't it?
Yes, sir. But so why you said that not always acceleration is means
Because
all
acceleration,
acceleration is a double differentiation of a function,
right?
and
But that double differentiation is a quantity that arises because of two things: change in the magnitude of the first derivative and change in the direction of the first derivative, right?
okay, sir, understood.
So I was appealing to acceleration simply because you have just cleared your 12th and you would have done all of this recently. So that is the only thing. Otherwise, I could have just defined it directly in this way, which is what basically most of the books in geometry do. But just to make it more palatable and more intuitive to you guys, I sort of brought in acceleration and velocity. Any further questions?
So it means curvature is the magnitude of the double differentiation.
Given the constraint that magnitude of the first derivative is 1, otherwise not. So you can see clearly here gamma, right? If I use this representation, it's not unit speed, right? Now if I compute the double derivative of this, what will I get? What is the double derivative of gamma?
Sir, r minus
R
cos t
minus
minus sin t.
And what is the magnitude of this?
R.
R.
It's r. So you can see it's completely counterintuitive. Right? It sort of gives us the idea that the curvature of a larger circle is larger.
Yes, sir.
Okay, understood?
Yes, sir, got it.
And feel free to ask. Okay, I mean, I'm in no rush to finish what I've decided to complete in the class. We have another class tomorrow, so in no particular hurry. Things are not clear, feel free to let me. Okay, so fine. If I'm given a representation of a curve where the speed is always 1, just take the double derivative. Length of the double derivative vector is my curvature. But what happens if I'm given a representation, right, where the speed is not always 1? Right? In that case, what can we do?